In this video, we're going to talk about ways to preferentially choose 1,2 over 1,4 or 1,4 over 1,2 when we're doing our addition reactions to dienes. So this is called kinetic versus thermodynamic control. So let's just kind of jump in with an example here so we can visualize the difference between kinetic and thermodynamic control. So what we want to look at is a reaction energy diagram. And remember, we start with our products. We're going to go through some kind of transition state, and we'll end up with our products. I think I might have said we're starting with products. We're starting with reactants, ending with products, going through a transition state. Okay, so for our electrophilic addition to dienes, we're going to have two options. One, we'll have a higher transition state than the other, but we'll end up having a more stable product. Second option, lower transition state, but less stable product. Okay, so if I wanted to think about speed, and let me actually change color of my second pathway here. There we go. So if I wanted to think about speed, which hill is going to be the fastest one to climb? The blue one, right? It's shorter, it's easier to get over. So if we're going to talk more technical, it means it has a lower activation energy. So there's the activation energy for for the blue path, and here's the activation energy for the red path. Remember, activation energy is typically with the delta G kind of double cross there. So lower activation energy means the reaction is going to go faster. So speed is what we connect to kinetics. That's what kinetics is referring to. So this is the one that's going to be under kinetic control or lead you to the kinetic product. So again, this is about being speedy, or the fastest option. If we look at the other pathway, it does have a higher activation energy, but we see that the product is more stable. So that means that our delta G of reaction for the red, make sure to make this red here, the red option is bigger, so delta G naught, than it is for the blue reaction. And that just means the product is going to be more stable. So stability of your product has to do with thermodynamics. So the red curve is your thermodynamic controlled option. And this has to do with stability. And the other thing we typically link with the thermodynamic product is that it is under equilibrium. You have to be under equilibrium to get there, because there's nothing stopping your reaction from taking the lowest hill possible. So a lot of your product is going to go up that short blue hill, reach blue product, but then if you let it sit long enough and heat it, give it enough energy to actually get over that red hill, it's going to back up and reverse, go back to reactants, and eventually climb up over that red hill and filter down to the low, more stable product. So if we look at a specific example here, again, we'll just look at our basic diene, and we'll add our one equivalent of HBr. We have the two possible products. We can have the 1,2 product, because the hydrogen is over here on the end, or we can have the 1,4 product, where the hydrogen's on the right end and the bromine is on the left. So at colder temperatures, which we usually kind of just estimate of being about 0 degrees Celsius, you will find that you'll get 71% 1,2 and 29% 1,4. So colder temperatures, you cool things down and you get more 1,2 products. If you heat things up to 35, 40 degrees Celsius or so, something above room temperature, you'll see that you only get 15% 1,2 products and you'll get 85% 1,4. So at 0 degrees Celsius, there's not a lot of energy in the system, so it can't get up over that red hill. It's going to have to take the easiest way out, which is our blue reaction. So that means at 0 degrees, colder temperatures, this is our kinetic control. So the kinetic control is going to favor the fastest reaction. For the, and I just realized I forgot my double bonds in my products there. For the heated reaction, so if you apply heat, you give it enough energy to eventually get up and over that bigger bump, the red pathway, and filter down to the more stable product. So that means we get more of the 1,4. That is our thermodynamic control. So let's remind ourselves why 1,4 is more stable than 1,2. For double bonds, the more substituted the double bond, the more stable it is. So if I look at the 1,2 product, I only have one carbon group coming off of the double bond, versus if I look at the 1,4, I have two carbon groups coming off of the double bond. So it's more substituted, more stable product. Therefore, it's lower in energy than the 1,2. So again, kinetic control, you need to cool your reaction down so it can only go over that easiest, fastest pathway. You will preferentially get the 1,2 product, which is the less stable product, but it's the one that's most easily formed. If you heat your reaction, you're under thermodynamic control. Your reaction can reach equilibrium, and it will favor the more stable product, which is the 1,4 product.